Now we will discuss about formation of standing waves and normal modes. Here, when we observe two opposite traveling waves of same amplitude and velocity and frequency, when they overlap, standing waves are formed. Why we call them as standing waves means they appear to be still and they are bounded in a region. So the standing waves cannot propagate, therefore they don't transport energy. So let us derive a mathematical relation or expression for the standing waves formed in stretched strings. So suppose a wave pulse is traveling through the string is given by the expression that is A sine kx minus omega. This is a progressive wave. And let us suppose the reflected wave of same amplitude and frequency is given by this equation kx plus omega t. If both of these waves overlap, stationary waves are formed. So let us apply the principle of superposition, according to which the resultant wave is given by, or the resultant displacement is given by algebraic sum of the displacement due to individual waves. So then we can write like this: y1 xt plus y2. So this is the algebraic sum of the displacement due to individual waves. So when you apply this, what you get is A is common, sine kx minus omega t plus sine kx plus omega. So let us make use of the trigonometric identity, that is sine a plus b plus sine a minus b, which is equal to 2 sine a cos b. So using this trigonometric identity, the above equation can be written as the resultant wave is given by 2a sine kx cos omega t. Here, this first part gives the amplitude of the resultant wave. So it shows that with respect to the position, that is x, from the reference point or from the origin, depending upon the distance of the point, the amplitude of vibration or oscillation of the particle is changing. So suppose if the amplitude is minimum, then sine kx must be 0, so that the amplitude is 0. For this condition, this kx must take values 0, pi, etc. So that means we can write it like this. So this is n times pi. Here, directly we can write in terms of wavelength, that is, since k is equal to 2 pi by lambda, therefore x can be taken as n times lambda by 2, where n stands for 0, 1, 2, etc. Suppose you have a string like this. If you consider this point as x equal to 0, when standing waves are formed at a distance of lambda by 2. So that is here. This is the position which is equal to at a distance of lambda by 2 from the initial position. So at this distance, you will get a point where the displacement is minimum. Such points are called as nodes. Such points are called as nodes. So similarly, if you have the displacement maximum, that is for sine kx is equal to 1, the amplitude will be 2 times smaller. For such cases, this kx must take values, that is pi by 2, etc. So we can say that in terms of wavelength, this x should be equal to n plus half lambda by 2. So that means for n is equal to 0, what we are going to get is x is equal to lambda by 4. And for n is equal to 1, you will be getting x is equal to 3 lambda by 4. In terms of wavelength, from the origin at distances of this is lambda by 4. And here this will be 3 times lambda by 4 distance from the origin. So all such points where the amplitude of vibration or oscillation is maximum, they are called as antinodes. Antinodes. So here is an example where I have shown stationary waves with 3 loops are formed between the 2 rigid points, and we are getting, of course, always the fixed points where the waves get reflected back. So they always will be nodal points, and in between we will have antinodes. So the points with maximum displacement or maximum amplitude in the stationary waves are called as nodes, antinodes. Those with the minimum amplitude are known as nodes. So in between the nodes and antinodes, for the different particles will be vibrating or oscillating with different amplitudes.